So I'm going to dwell now on this subject of quantum simulation. And in particular, I'm emphasizing the term universal quantum simulation. So I mentioned this morning that the topic is very hot. And if anybody had a chance between my morning lecture and now, you'd see that the Baluta and Nori paper talks about two categories of analog and digital simulation. And I'm very fussy about these terms. So in my view, there's only the universal quantum simulation, which was the type that Feynman put forward, Seth Lloyd discussed, and so on. So I'm going to focus strictly on the idea of a quantum simulator that has algorithms to solve computational problems on a universal quantum computer. And I'll make that clear. So let me first give you the idea of what the purpose of the quantum simulator is. And often it's not so clear in the literature. And the idea is simply to solve Schrödinger's equation. So the idea is that for various reasons we want to solve quantum systems. And to do that, we want to be able to solve Schrödinger's equation. If we get into relativistic effects and quantum field theories and that, there is work going on. For example, there was a nice paper out in 2012 by John Presco's group dealing with quantum simulation of quantum field theories. I'm not going to go into that. I don't have enough time in these lectures to cover it. So we'll just deal with non-relativistic quantum mechanics. So all we want to do is solve Schrödinger's equation. And Schrödinger's equation is written in the following form that you're familiar with. The time derivative of the wave function times the square root of -1 is a Hamiltonian times the wave function. And we're going to make assumptions that are not necessary overall, but it's going to make our life easier in this lecture. We're going to just assume that the Hamiltonian has Hermitian, and therefore the dynamics are unitary. I said that we want to solve Schrödinger's equation, but what does it mean to solve? There are different things to solve. We might want to know how the wave function evolves over time. We might want to know the spectrum of the Hamiltonian. We might want to know the ground state or some other property of eigenstates. So there are different questions and different problems that can be posed related to Schrödinger's equation, and different problems have different methods of solution and different complexities associated with addressing them. So we need to be very careful when we say we're going to solve Schrödinger's equation. What is it we're going to solve? And the different questions have, each one of them is interesting for different purposes. So I've listed them down. This is solving the time-dependent wave function, which is actually the one that I'm really going to care about here. That's the one we're going to deal with. There's determining the spectrum of the Hamiltonian and finding eigenvectors such as the ground state. So those are three very common ones. This morning, when I was quoting Feynman, I was talking about Feynman. So in Feynman's approach, he's essentially saying, would a quantum computer efficiently solve quantum systems in that it would deliver expectation values of observables as they evolve over time? He didn't say it in those words, but if you read the paper carefully, you can see that he clearly meant it would solve the time-dependent observable, some time-dependent observables. And solving Schrödinger's equation is actually very important. In chemistry and physics, there's a lot of papers coming out now on quantum simulation used for chemistry purposes. Not so well known in the physics community, but they're published in places like Nature and that, so they're getting a lot of coverage. This one I'll get to a bit later on coupled linear equations and coupled differential equations. It turns out that if we have a quantum simulator, it's not just useful for solving Schrödinger's equation, it's useful for solving other differential equations. Remember, Schrödinger's equation is just a wave equation. So if we can solve a wave equation efficiently, we might be able to solve other wave equations efficiently. So the techniques I talk about might have value beyond just solving quantum systems. It might be the case that we can solve, that it might turn out that a quantum simulator is able to solve general linear coupled equations. And I'll get to the paper by Harrow, Hasidim, and Lloyd that came out in PhysRev Letters in 2008 that showed that a quantum simulator would solve coupled equations. Dominic Berry later showed that you can generalize that to solving large systems of differential equations. So the question somebody asked me earlier about what's a quantum simulator as opposed to a simulator, it's always good to ask that because it's just a simulator. A quantum computer is just a computer. A quantum simulator is just a simulator. So when does the quantum kick in? The quantum kicks in when the classical computer or the classical simulator is just not good enough. So we find resources that allow us to do things we can't otherwise. So here, let's see what the limits are with the classical simulation. So if we want to solve Schrödinger's equation in some sense, the way we would like to do it is, one way to do it is to diagonalize the Hamiltonian. So if we diagonalize the Hamiltonian, we can, then we have the eigenvectors, the eigenvalues, and everything is trivial. It's kind of an undergraduate physics problem. You know, you give a 2 by 2 Hamiltonian, diagonalize it, and then you've got the solutions for all time. However, diagonalizing the Hamiltonian is a very hard problem because the Hamiltonian goes by dimension of Hilbert space. So it's the dimension d of Hilbert space by d, so it's d squared. And then, I mean, there's hermiticity, so it's slightly smaller. And then, so it's size d squared, and d is exponential the number of qubits. So a problem size is the log of dimension. So the dimension is an exponential of the log of dimension. About 11 years ago, there was a lot of fuss about adiabatic quantum computing. And adiabatic quantum computing is still controversial today. But the idea of adiabatic quantum computing is simply that you start off, you say, well, you start off with a Hamiltonian, some Hamiltonian whose ground state could be all zeros or an instance of a problem, but all zeros, and then it would adiabatically evolve to a new ground state that would be the solution to the problem. And so adiabatic computing looked extremely powerful. At the time, the group that was at MIT was saying that adiabatic computing was so good it would efficiently solve NP-complete problems. And so everybody became very worried about this because the claim was too strong. It was something that it wasn't believable, but it wasn't obviously wrong. So it provoked a lot of thinking. So that's kind of the motivation for considering what Hamiltonians are not efficiently simulatable. And, and so Andrew then wrote down a set of rules. Later I'm going to make these rigorous, but his set of rules that appear in his thesis are the following 4. He says that if the Hamiltonian is a sum of Hamiltonians, each acting on a constant number of qubits, then it's simulatable. So O1 is order 1, it just means a constant. But physically it's very sensible. If you consider a condensed matter system, for example, nearest neighbor. So suppose you write down a condensed matter system where every particle interacts with 4 neighbors. Okay, then you can have 100 or 1,000 or 10,000 particles, but they always interact only with 4. That's an example of order 1, right? So he's saying any Hamiltonian that can be written as the sum of Hamiltonians that act on a constant. So you just write down the Hamiltonian term for each element acting on 4 neighbors, that can be efficiently simulated. Or it's square root of -1 times the commutator of simulatable Hamiltonians, or it's related to 1 by an efficiently implementable unitary conjugation, for example, a Fourier transform. So if you take Hamiltonian, you Fourier transform it, or discrete Fourier transform if you like. If that can be effected efficiently, then it's still efficiently simulatable. And also it has to be sparse and efficiently computable. And that kills the example of a very hard problem because the Hamiltonian matrix elements themselves have to be efficiently computable. So you can't sidestep the fact that in order to simulate a Hamiltonian, there has to exist an efficient classical algorithm to compute the matrix elements of the Hamiltonian. So that was a set of rules that he laid down, not rigorously proved. And I'll get to the point where we get to Aharonov and Tashma and what they showed. So, but if these are met, then the Hamiltonian is simulatable efficiently. So let's now Sure.
Does that rule out finding critical points of Hamiltonians where the correlation length goes to infinity?
Okay, so the question is, does it rule out Hamiltonians where the critical
points where the correlation length is
So I don't know the answer, but in classical simulatability, you probably know this, that there's an entanglement length, right? So if the entanglement length grows logarithmically with the size of the system, then you can use density matrix renormalization group to be able to do it. If not, no. But in this system, I don't know the answer. I don't know. Okay, so now let's deconstruct the words. I've been using a lot of words here, and so let's be very careful. So the problem statement is that we want to construct, and this kind of goes back to Feynman. What does Feynman mean when he says that a quantum simulator can efficiently simulate a quantum system? So this kind of work I've done and colleagues, including Richard Cleave at the University of Waterloo. And so we construct a problem statement so it's clear, at least we're clear on what we think he means. So we think it means that that the task is to construct an efficient quantum algorithm for accurately simulating the evolution of general quantum systems. And so let's understand what each of the words mean now in the problem statement. When we say that it has to be efficient, it means that there's a polynomial overhead. And that means that it's polynomial with respect to the problem size and with respect to 1 over epsilon, where epsilon is the allowed error on simulating the evolution of a quantum state. The quantum algorithm, so the algorithm essentially has an input, an output, and an instruction set for a quantum computer. So that's what I mean by a quantum algorithm here. It has to be accurate, which means that it's a pre-specified, i.e. an input to the algorithm that says that there's some allowed error epsilon. This is not true in any existing experiment on quantum simulation. They are not yet inserting epsilon as an input. So the problem statement that we have here for accuracy doesn't yet match what experimentalists do. So naturally, I mean, I'm happy with what experimentalists are doing. I'm happy for any progress whatsoever. But in terms of relating it to the origins of quantum simulation, there's still a gap, I think, in the understanding. So the point I'm making, I think, is very important, but not everybody listens to my message. Okay, and that if it's going to be efficient with respect to the bounded error, there's no worse than a polynomial overhead in 1 on epsilon. And then we're going to assume, we don't have to, but we're going to assume that it's isolated in quantum, so the system dynamics are given by a Hermitian Hamiltonian generated evolution. And finally, that it's general. And so in the way that it has to be general, in order to solve that problem, is we introduce an oracle. So the oracle is something that holds the Hamiltonian. So the idea, the way we think of what Feynman said, is that if there's a quantum simulator that efficiently simulates a quantum system, that means there should be a quantum algorithm written before you know the Hamiltonian. You see? So a question I often get is, well, you know, given a particular Hamiltonian, what can you do? Well, that's one kind of problem. But what we're going to go into is, does there exist an algorithm that will efficiently solve any Hamiltonian evolution with reasonable assumptions on the Hamiltonian, like Child said, such that the algorithm is going to work by querying the Hamiltonian. So the Hamiltonian is kind of inserted later as a subroutine, and then you count the cost of every call to a subroutine as a cost. In computer science, the subroutine is an oracle. I know there's a lot there. It's kind of deep, but this will go into it, and I hope it becomes clear. Okay, so now let's cover first what Lloyd did. So Feynman's paper came out in 1982. Then Deutsch's work on the quantum Turing machine was about 85, 86. And then it was 1996 that Lloyd came along and said, I can now prove Feynman's conjecture. Let's understand what Lloyd did. Lloyd focused, he assumed a lot of stuff. He assumed that the Hamiltonian had a tensor product structure and various other stuff. So he proved it, but he made a lot of assumptions along the way. And the key step that he did is he dealt with the evolution by saying it's not a continuous time evolution, it's discretized. So it's moving from continuous to discrete time. And the way that's done, I mentioned at the beginning that one way to solve Schrödinger's equation is product formula, and I said we were going to go into it. So let's talk about it. This is the Lee-Trotter product formula. If you look in Nielsen and Chuang's book on quantum information and computation, the big Bible of quantum computing, you'll see that there. And the most basic form looks like this. The idea is that we take e to the it, sum of two operators that generally don't commute with each other, and if we let n go to infinity, so we essentially chop up our time into intervals and take that product and let it go to n, we'll get convergence with an error. Most physicists don't worry about the error so much, it's just close, and we tend to take asymptotics without counting errors. But once we go to the computer science side, we can't do that. We have to count all the errors in the convergence because we have to count the resources. So the asymptotics we use in physics are dangerous in computer science. We lose track of resources that way. Generally, that's if the Hamiltonian is time independent, etc. Generally, we could consider a time-dependent Hamiltonian and break up a Hamiltonian into a sum of Hamiltonians and then wind up getting a time-ordered exponential of an integral and write it out as some product. So this is kind of the ultimate generalization of that. I probably won't have time to get into it. In my group, we've done assessments of the time-dependent Hamiltonian, in particular because I care a lot about the adiabatic quantum computing and what goes wrong. So the idea you can see here is, in order for me to see how the adiabatic quantum computings work, I want to write a quantum simulator. So I'd like to simulate adiabatic quantum computing on a quantum Turing machine. Okay, so this goes back to Lloyd's paper in 1996 in the journal Science. And that's what he states, that he proved Feynman's conjecture. And so the idea is that he breaks up, he shows that he gets n iterations of breaking up the evolution into a product. And he cares that there's a polynomial function of r, m, and n. So let me explain what these are. But first of all, I mentioned he assumed a tensor product structure. We don't do that anymore. So we don't assume a tensor product structure. There's a lot of gifts you get when you do the tensor product structure. This was discarded as quantum walks became very important. Ashwin, who spoke before me, did some of the seminal work on quantum walks, and this kind of thinking drove a lot of consideration about how to deal with Hamiltonian evolution without tensor product structure. He assumed that the Hamiltonian was time independent, which is a severe restriction, and in his paper, okay, so I don't want to be very negative, but I need to point out the drawbacks. In the paper, he claims a runtime, which is order t, but if you go through the argument, it's clear to see that it's actually an order t squared. So the claim in the paper is not actually what the algorithm cost. The space cost was order n, and so, but it just points, like again, just like Feynman, when he said things, they weren't that clear. Lloyd, when he did it, was a pioneer, and some of the concepts still needed to be clarified. That came years later. But here's the idea that Lloyd had. If we write the evolution operator, so we have a Hamiltonian, and we break it up into a sum of Hamiltonians, each one that generates a quantum gate that we can make in our quantum computer, then we write it as a product in this form, and I'll explain better later, but R is the number of time intervals. We run for time t, break it up into R intervals, and then each of these Hamiltonians generates a gate. And I'll show you what the gates are. And then we take that to the power of r, and that's our approximation. Then, when we calculate the error, there's the t squared term that comes out of a sum of mutual commutators between non-commuting Hamiltonians and another error term. And that other error term you have to keep track of. And so that's the key element of Lloyd's paper in 1996, showing how that works and explaining that each of these generates a gate that can be done in unit time on a quantum computer. Later, so Lloyd did his work in 1996. It was before the big fuss about adiabatic quantum computing. So when adiabatic quantum computing came along, the question of quantum simulation needed to be revisited. It became very important. So, and then this is where the computer scientists had to come to the rescue. Aharonov here, by the way, is not Yakir Aharonov. It's his niece, Dorit Aharonov, who's in computer science at the Hebrew University in Jerusalem, and Tashma, who's at Tel Aviv University. And they had a beautiful paper, which appeared in Stock 2003. I find it a very hard paper to read. It took me years to get a good understanding of it, and it's still not perfect. But I'll give you some highlights of it. And there's a long version on the archive. So you want to read the archive version. It's very long, actually not terribly well written, but very complete. You know, that kind of every time I read it, I've read it many times, every time I read it I get more insight. And so they were motivated by the issue that an adiabatic quantum computer was being claimed to solve efficiently problems that were NP hard. So NP hard, or at least as hard as NP. And this is the claims were just simply not believed at the time. And the question of which states can be efficiently generated arose. So the idea, the way that they started looking at the problem is not which Hamiltonians can be simulated, but if you're going to map a state which can represent a problem, input of a problem, and another state that's an output. Remember, the algorithm has an input and output. can the output be generated from the input? You see, so the kind of thinking is what states can legitimately be generated. And what they proved, to cut a long story short, is that the quantum simulation is equivalent to a class of problems in computer science known as statistical zero knowledge. So every instance of a problem in statistical zero knowledge has a counterpart in the area of quantum simulation. And examples of statistical zero knowledge include the discrete logarithm, which is important for communication security, quadratic residuosity, and the gap closest vector in a lattice. So these are hot areas of research, and they're all related to it. So once they established that the problem of quantum state generation, which is the essence of quantum simulation, is equivalent to statistical zero knowledge, then some very strong statements can be made. And I'll show you a lemma they have, which is important. So I told you about Childs' work, and Andrew Childs, when he said what is reasonable to simulate and what isn't. But through this approach, Aharonov and Tashma were able to make a strong proof. And here's the, for the purpose of these lectures, the key element I want to dwell on in their paper is a lemma, and it's what they call the Sparse Hamiltonian lemma. And this puts the rigor into what Andrew Childs was talking about. So they show that if a Hamiltonian, given a Hamiltonian that's d-sparse, so let me explain what sparse is. So remember that a Hamiltonian you could think of as a matrix. And the size of the matrix is exponential in the number of qubits. So if you have n qubits, your matrix is 2 to the n by 2 to the n. If you have to write down an exponential number of elements, you're going to be in trouble. So the idea is that if it's d-sparse, it means that if you have a 2 to the n by 2 to the n matrix, no more than d elements in any row or column is going to be non-zero. Okay? So it means that in any row, your row grows exponentially with your problem size, but only a polynomial growth is seen in the non-zero elements. So that's the idea of d-sparse. In general, d is also a function of n. So if n is the number of bits specifying the problem, you expect d to grow as a polynomial function of n. You see this, for example, if you solve a Heisenberg Hamiltonian or very other common basic Hamiltonians in condensed matter physics, and you write out the matrix, you'll see that it's d-sparse, that there's a polynomial growth in the number of non-zero elements, even though the matrix grows exponentially in size. So the number of non-zero entries is polynomial in n bounded. And if the Hamiltonian is row computable, means that every element can be computed efficiently on a classical computer, relating to what Andrew Childs said. So there's an algorithm that can efficiently compute the list of non-zero Hamiltonian matrix elements in any given row. And if the norm of the Hamiltonian is bounded above by some polynomial function of n, then H is simulatable. So this is the rigorous statement in Aharonov and Tashma. If this condition is met, then we have an efficient simulatability condition, and we know it works. So it answers the problem. I mean, this, in a large sense, this is the answer to Feynman's problem. That as long as these conditions hold, a quantum simulator is guaranteed to give an answer to the evolution question, and therefore the question of what is the expectation value of observables. And in their approach, they didn't care about making it too elegant. They just wanted to show efficiency. It's not explicitly stated, but you can go through the paper and figure out that their algorithm has a runtime that goes as the order of the 9th power of n, 4th power of d, and remember d is a polynomial function of n as well, over epsilon, and it's order t to the 3/2. The t to the 3/2, remember that Lloyd had order t squared. He claimed order t, but it was order t squared. And theirs is order t to the 3/2, and they brought that down by doing a symmetrization of that Trotter formula, and we'll go into it. So that's what they had. So they, in my view, this is really the rigorous solution to Feynman's statement. Although Lloyd's work deservedly gets a lot of attention, This paper doesn't, and yet I think it's, like, to me, it's the one that I get the satisfaction out of. And so that was in principle. But nowadays, we're in a situation where we want to make quantum simulators, and ninth powers of things are too big for us. To a computer scientist, ninth power of n looks very nice. But, if you start plotting the ninth power of number n, the curve rides very fast. So it's awful if you want to start making things work. And even the order of the t to the 3/2 might be worth trying to solve. So one of the efforts that then followed this was how to get these costs down. So then you say, well, okay, that's efficient, but can it become more efficient? So this is just above. This is the time and space cost for Aharonov and Tashma that you just saw. Time cost here, space cost is order n. Andrew Childs, in his thesis, writes, he suggested a way of improving the time cost, and he did also the symmetrized Lie-Trotter formula that they did for the t to the 3/2. And what he did is he started bringing in graph theoretic techniques to try to improve the algorithm, and I'll explain how this works. And so the idea is that if you want to have a better simulation algorithm, then you can make the Hamiltonian matrix into a graph and start coloring the graph. And I'll explain it because it's important if we're going to start running quantum simulators. And in so doing, he took the cost. So d to the 4 went to d to the 4 plus little o of 1. It means that it grows roughly as a constant. There's something like a log power of root t or something there. But you can think of it just like a small constant. N squared t to the 3/2. So you see the n to the 9 went down to n squared. D went up a tiny, tiny bit. Epsilon went to a root epsilon. It's in the denominator, so that's not so good. And then S goes as order n. He didn't change that. And then there was some work I did with Dominic Berry, Richard Cleve back when he was at the University of Calgary. He had a student, Graham Ahokas, who did the beginning stages of the work on this. And our work, which was out in Communications and Mathematical Physics, brought the cost down as follows. And so what we were able to find is that we were able to bring the time cost down. N squared went to log star n. I'll explain that. K can be as large as you like. So t effectively becomes a constant. T becomes 1 plus little o of 1. And we have epsilon to the 1 on 2k. So k can be very, very large. So it's a denominator with a very large root of a small number. And our space cost went up very slightly. And you see the log star n there. And probably most of you don't know the log star n. So let me explain what's going on. It turns out, so let's say that I asked you the following question. Given a number of x, what is the size of a tower of powers of 2, the smallest tower of powers of 2 that exceed that number? So if I take the number x, can you see that at the back? X? Hello? Anybody see it? Good, okay. And then you ask something like, what is 2 to the 2 to the 2 to the 2? This is what I mean by the height of that. And you say, what is the shortest height of a tower of powers of 2 that would be greater than or equal to x? Okay, so what's the biggest number you might think of in physics? 10 to the 80 maybe, something like that? So anybody have an idea how tall that tower would be? Guess. What? 4 or 5, yeah, good guess. Okay, so maybe up to 5. 5 would be huge. 4 maybe are on the boundary, but that's right. So it doesn't get very tall. And so the log star n is really that. It's just, so when we see the log star of n, it's just given n as the number of qubits, what is the smallest tower of powers of 2 that exceed that number? So log star n is very small. You know, if you start getting to cosmological scale number of particles, you're still on 4 or 5. It's tiny. It's even better than a constant. A constant could be huge, and this is a small number. So it effectively brings the cost down a lot. And then here, it grows the space cost slightly but it's almost like growing it by a constant factor, which is already thrown away in the order. So, that's kind of the idea I want to get to, is how to bring the cost down. And bringing the cost down are extremely important if we're going to get nearer term quantum simulations to work, because every qubit and every gate is expensive to us. So we have to bring that down. So let me go into how this works. And we have here a Hamiltonian, and let me explain what each term refers to. So we have a Hamiltonian for a system, and we want to write it as a sum of Hamiltonians. So we're saying, given the Hamiltonian, we want to solve its evolution. Let each AJ be a Hamiltonian that generates a gate. So suppose that we can do, and I mentioned this morning, the Hadamard gate, that R gate are two gates that we might want to be able to generate. So in given time, we might have two different Hamiltonians that will generate those gates as exponentials. And so here's the gate. Each gate is generated as an exponential. We can have an exponential that will generate a C0 gate. But in the movie I showed, and also what Steve Lyon talked about with the Lawson DiVincenzo scheme, their scheme has a root swap. The movie I showed you had a root-root swap, so the fourth root of swap. And and in the movie I showed you, we turn on an electric field for some time and turn it off. So the idea is it has a Hamiltonian. So when you do it and you want to generate like the square root of swap or the fourth root of swap, you have a Hamiltonian. That corresponds to turning on electric fields and magnetic fields. Leave them on, turn it off, and you generate a gate. So you get the idea that each one of these HJs corresponds to a gate that we can create in the lab. So to the physicist, the Hamiltonian describes the interactions we need to get something to happen. And then in the computer science side, this is the gate we get. So the gate is just an exponential of the Hamiltonian, which is what we can do in the lab. And here, we're going to consider that time is fixed. So each gate corresponds not to running it for some arbitrary time, but you push a button, and your time is predetermined. Right? So if you're going to make a gate, you figure out how long it's going to run, but then when you want a gate, you push a button and make that gate. You want a different J, you push another button. So, the idea is that you're going to have a sequence of gates. I showed that in the movie. When you saw that dance going on, it was just a set of gates all taking place in a row. And you'll hear more about it, I guess, certainly when Ray talks about NMR. It's a sequence of pulses. Each pulse is generated by some Hamiltonian. And here, in order to start talking about the coloring, graph coloring algorithm, when we talk about each kind of gate generated by a different Hamiltonian, let's talk about that as a color. J is the color index. And here we have M colors. So M is the number of different types of gates we can make, each generated by a different J, and we'll just think of each one as having a different color. Then what we want to do, and this goes back to what Seth Lloyd did, what Feynman hinted about, what Aharonov and Tashma made rigorous, is we want to take the Hamiltonian and we want to be able to take the evolution operator and write it as a product of evolutions, each one corresponding to a different gate. So if I have, now in the color language, I've got my red gate, blue gate, green gate. So in order to do my quantum circuit, I might hit, just imagine colored buttons. Red, green, blue, green, red, I'm just hitting that. So the way that we approximate the evolution is we read this, it would tell us the order of colors, and then you just hit the colored buttons according to that sequence. So that's what we want to get our simulation to, is to be able to do that. And then that should approximate this, and we want to make sure that the number of times we hit the button, so the length of the sequence is the number of times we hit these colored buttons, and we want to make sure that the number of times capital N we hit it doesn't grow exponentially. So if you have a problem with little n qubits and big N number of times you hit a button, that has to be no worse than a polynomial function of that size and of 1 on epsilon. Okay, so here I'll give you an idea of how it works. So what we're going to do is to let each HJ be one sparse. So we're going to discover. I'm going to show you now how you can make a circuit that will run if the Hamiltonians are one sparse. So then what you can imagine is you have a set of one sparse Hamiltonians, and that's the number of colors you need, right? So the number of buttons, number of colored buttons, is the number of one sparse Hamiltonians. And so to begin with, I took this picture out of Andrew Child's PhD thesis, and this one shows a circuit for simulating a diagonal Hamiltonian. So a diagonal Hamiltonian is one sparse. It's only got one element in any row or column, and it's always along the diagonal. So if we have the Hamiltonian and it's diagonal, I just write D of A. A is the index for a particular row or column. So if we take the 8th row, 8th column, and take the matrix element in that element of the diagonal, and it's written as a bit string of length k, then, and if this can be efficiently, it's important that it can be computed efficiently classically. So it's a diagonal matrix, and every diagonal element can be computed by an efficient algorithm on a classical computer. Uh-oh. This is going to keep happening now. Oh, I'll just let it happen. Okay, so here's the way the circuit works. So we have a function that for given A as a qubit string, these are ancillary qubits, and then the idea is that the D of A, so this D is this function D, it writes the value of A on all those qubits. So it's a K, this is a K-bit string, so if we have K qubits here, it just writes A as a bit string on those different qubits. That's the first step, and we can do that efficiently. Then the second step is we let each one of these evolve so that this qubit evolves according to e to the minus it projector onto 1. That projects, each one projects onto 1. So if that qubit is in the 1 state, it picks up a phase, and if it's in the 0 state, it doesn't. So this just imposes a relative phase between the 0 and 1. Same here, but you can see that these go up by powers of 2. And then we apply the D again, and the reason we apply the D again is it returns all the ancilla back to zeros. Remember what I said, in a quantum computer you have to recycle everything. So this recycles it back to a string of zeros, and the result, these were just controlling, but the result is that A then maps to a phase factor of itself, and this is just that Hamiltonian evolution acting on A. So that circuit does the job. You could do the calculation yourself, it's not hard, and verify that it works. And then of course, in a quantum computer, you don't have A in some basis state. A is a superposition. So you let A be a superposition of all row elements, and then the output is you have the evolution acting on the superposition of all diagonal elements. So this circuit, which turns out to be efficient, is the way that we want to simulate evolution of a diagonal Hamiltonian. Now we don't want, I said we can do any one sparse Hamiltonian, and then I show you for the diagonal, but then the idea is that it's a simple extension to an off-diagonal one sparse Hamiltonian. So if we have a one sparse Hamiltonian, i.e. no more than one non-zero element in any row or column, there was work that came out also in Stock 2003, the Symposium on the Theory of Computing, same one as the Aronoff and Tashma work, and Childs, Cleve, Diallo, Fari, Gutmann, and Spielmann developed the circuit I'll show you on the next slide, and they essentially used this circuit to simulate any evolution by a one sparse Hamiltonian, and I've kind of compressed it a bit. We have two strings, A and B. I didn't have time to get it. I was kind of playing with it earlier and got too tired. But we have a set A and a set B, and if we consider a matrix which has the symmetry that given any A or B strings, that T on AB and all zeros in the ancilla equals this, and if we have T of AB with 1 equals 0, there exists a way of being able to do it. I won't go into the details, but essentially there's a transposition that takes place. These W's transposed. A1 is the first element of string A, AN is the last element of string A. Same with the Bs. There's some transposition, and then a circuit that takes place, which is similar to the one I previously showed you. Then the W daggers, and the result out here is that we wind up with the evolution out here that corresponds to the evolution for the one-sparse Hamiltonian. So experimentally, we have this map. Once we can start writing these things, we now have exactly the circuits we require to be able to do the experiment. So I can go to an experimentalist, if they get the capability of dealing with enough qubits, I can go to them and I can say, okay, this is the pulse sequence you need, or this is the way to align your quantum dots, or whatever it is. Like this, once we get to this circuit level, we have exactly the information we need to translate that into experimental implementation. So now, all I've shown you is how to solve the one-sparse Hamiltonian. Now we have to go to a general d-sparse Hamiltonian according to the Aharonov and Tashma model. And so here, so when I'm saying solve Schrödinger's equation, you remember that's solving the evolution of the state, not the spectrum, not the eigenvectors, it's the evolution. We have our color index J nu, so we understand we need to do a sequence. We have. If you speak louder, I can hear you.
If you have a d-sparse Hamiltonian, you can always diagonalize it to one-sparse Hamiltonian.
So I think the question is, if we have a d-sparse Hamiltonian, can't we always diagonalize it? Well, the answer is yes, but not efficiently. So our goal here is not, our goal is to do things efficiently. Okay, so then we have, because you remember the diagonalization I said was exponential in overhead, right? Yeah. Okay, so then we clean up the ancilla, we repeat the process. Let me show you the picture. So here's the picture that represents what Aharonov and Tashma proposed in their stock paper, also the same paper as the d-sparse, as the sparse Hamiltonian lemma. And so the idea is that they feed in, so L is the basis set. So the wave function, it's an arbitrary wave function, which can be written as a superposition of strings of zeros and ones. So the basis set is just what we call the computational basis. Strings of zeros and ones. It comes in, and then we have our ancilla. The first step of their circuit simply writes in X and Y, which are row and column elements for the Hamiltonian, and then it determines whether the Hamiltonian is zero or non-zero for a particular color. So we want to be able to develop a circuit that will, so each of these Hamiltonians that are one sparse, we think of as a different color, because that generates the colored button that we're going to push. And then we want to know whether we should fill in a string of qubits corresponding to an approximation to the matrix element or not. And it's a color check. So in the previous slide I showed you, in the previous slide, not the second previous slide, here, the idea here was this turns out to be a color element that we're able to determine whether we want to do an operation or not. Don't have time to go into all the details. But this writes in the row and column for the Hamiltonian matrix element, the matrix element itself. Then it goes through, this is a one-sparse Hamiltonian. Then at this point, this is the cleave, etc. Scheme, including the cleanup phase over here. And so the Aharonov and Tashma scheme has a way of establishing, of taking the evolution and turning it into a sequence of evolutionary steps generated by one-sparse Hamiltonians in that fashion, and this is the way their circuit operates. Okay, and I won't go into it further. It's just kind of giving you the idea that there's a way of doing it. But if we take the Aharonov and Tashma scheme, we're able then to write these boxes that are then broken up into that cleave, childs, etc. Method. And so again, we're still able to write all this down in circuits and go to an experimentalist and say, okay, here's the way you do your simulation. So we have a way of designing quantum circuits. And I've got down here, this is complicated, I won't go into it, but this breaks down one of the steps in the Aharonov and Tashma, so we're able to break it down into a sequence of gates in order to be able to implement the evolution. These are all single qubit operations, and these are things like controlled knots, double controlled knots, and so on. If they're black, it means no action. If it's 0, enacted if it's a 1, and if it's an empty circle, this is the way we do the reverse. If it's in 0, we do something, and if it's in 1, we don't. So it's kind of the negation. All right. So now I mentioned to you about the Aharonov and Tashma had the t to the 3 halves scaling. Lloyd had the t squared. And so back in Calgary a number of years ago when I was talking to Richard Cleve, he was telling me that his intuition as a computer scientist was that t to the 3 halves was too big. But his intuition was that t would be too small. So the idea is that the cost should be able to be brought down. And I know we'd had a conversation with Andrew Childs at the time, and the idea is it should be brought down, and the technique should come out of improving the Trotter formula. And so Masaru Suzuki, who's a mathematical physicist in Japan, he developed techniques on ways of dealing with exponential operators. It's very interesting. So when I'm talking about an evolution operator, I take e to the minus it times some operator. It turns out that these expressions are analytic, which means that time doesn't have to be a real number. You can make time complex. And so the techniques that we care about for operator ordering work whether t is imaginary or real, with certain subtleties about convergence. And Suzuki was interested in getting ground states. So if you want to get a ground state, you don't want an evolution operator, you want kind of a damping operator that effectively cools the system. But on a mathematical level, the technique that you use to be able to decompose the operators doesn't care whether time is real or imaginary. So Suzuki's methods are directly applicable to decomposing the unitary evolution and extending the Trotter formula to higher order. So we took Suzuki's formula, which worked effectively for imaginary t, and turned it to a real t. And here's the idea. So the abstract specifies this, but it's too small for you to read. So the idea is that in Suzuki's paper, if we take e to the x a plus b, so remember, before I talked about it, but x can be real or imaginary or some complex number. And then what he showed is an iterative formula. So he essentially said if you take some order, he's able to get a product of exponentials of a and b, and get, and this would be a function, so in my case I think of t, x is like time, and then get an order correction that would go like order to the t m plus 1, where m is the mth iteration of his particular formula. And then when you do that, you just have here e to the something times a, e to the something times b, e to the something times a, e to the something times b, and so on. So if a and b are the two colors, it's like two color buttons, right? Push this, and so on. And it all has to be a symmetric one, so it turns out that you sandwich a's and b's together, and that delivers an improvement, and so you get this formula. Then if you say, well, instead of going for time t is long, let's do the trick of breaking it up in intervals. You make small intervals of size, so n intervals, I used r before, but n intervals in this abstract, then we have a way of breaking it up. So we want to find a way of saying we want this evolution, we want to hit these colored buttons in the right order to reduce the number of times we hit them. Because every time we hit a colored button, that's like doing a gate in an experiment, and gates and experiments are expensive.
Where does the independent come from on the right hand side?
You mean here?
Yeah, the second line.
So you're asking Sm of x, where does x come in? I'll have to show you. It will come up. Essentially, x is like the time, right? So if you think of the Hamiltonian as a plus b, x is like the time or imaginary time for the system. So it's just a parameter you plug in. Is that what you're asking? And then
Yeah, so is the sum of t is related to x or something? And then
No.
the second equation.
no, I'll show you. I'll go to it. Yeah, it's not that simple. Okay, and so the way I'll show you is I'll start with the simpler example first, and that's the Trotter formula. So the Trotter formula, which is the one in Nielsen and Chuang's book, is the most trivial form of it and very straightforward. And so if we take the Hamiltonian as a sum of Hamiltonians, each one generating one of those colors we use to hit buttons, then if we take the lowest order, we get the Trotter formula in Nielsen and Chuang's book. and then we're able to take, and now instead of x, I'm writing it, e to the iht in the symmetrized form has an h1 on the left, an h1 on the right, h2 in the middle, and this time is half of this time. Does that answer your question about x now? Okay. And then, I haven't analyzed the error yet, but there's an error, and this is what we care a lot about. And then it turns out that if we use the symmetrized Trotter formula, the number of exponentials required to be able to reach some error epsilon goes as t to the 3/2, and that's the t to the 3/2 that you see in Aharonov and Tashman's work, and also in Child's work. So what we want to do is to take the Hamiltonian, and we have a sum, and then, what we want to do is to generalize the formula. So we have two generalizations. One is instead of h1 plus h2, we can have m of those. And the second thing is that instead of this symmetrized formula, imagine making it bigger. So like you have e to the h1, h2, h1, h2, h1. That's the idea that Suzuki had. He said, instead of just having a sandwich of h1s on each side and an h2 in the middle, why not make a longer product in the middle? Will that help? And so the idea of his algorithm is to try to make it as efficient as possible to break up this product. So the Trotter formula, if we go from h1 plus h2 to a sum of many, can be written in this form. Now I've switched back to Suzuki, but I'm using lambda instead of x. And then, if we know the solution for 2, we can get S4. It always goes up in even steps because we have an iterative formula to be able to calculate. And there's quantities, pk, and so on. So pk, k is the order of the Suzuki expansion, and it's simply an algorithm that we use here to be able to calculate it. So we now have an iterative algorithm that we can calculate higher order Trotter formulas to any order. Okay, so that's what Suzuki showed. And that's what Suzuki showed. And in his proof, he shows that his kth order approximation to this, again, he was worried about finding ground state, so it's kind of lambda's real in his case, was order lambda to the 2k plus 1. He wasn't worried about quantum algorithms. That was far from his mind at the time. Having an order expression is not good enough to be able for us to put a bound on the resources in order to prove efficiency, but it's the right start. And if you go to higher and higher order, lambda is going to be small because it's small time intervals. It's the order of some small number to the power of 2k plus 1. So we have his formula, but his formula has to be shown to be valid for lambda as being imaginary, and the order expression must turn into a less than or equal to. We have to have a strict inequality. So we did that work a few years ago, and just to give you the idea, I won't go through any details, and I'm going to stop in a minute. Yeah. So skipping a lot of the details there, writing it again in terms of time t, we're able to show that we can bound the difference between a Suzuki approximation with order k and the actual by some scaling with time, and effectively show, just see if it's on the next slide. Yeah, the next slide, we're able to show that the time cost, the number of times we hit those colored buttons, so tau is a scaled time. So in theoretical physics, everything should be dimensionless, even time. So its scaled time is done with respect to the norm of the Hamiltonian. Right? The norm of the Hamiltonian tells you how fast things change. So if you want to get rid of dimension in your time, you just think of the Hamiltonian as being a rate term. You find the worst rate, and then you take your rate times the time, and that's dimensionless. So we have a dimensionless time, and for k very large, you can see that the number of times we hit the colored buttons is almost linear in t. Okay? So that takes it down from t to the 3/2. And then there's different things you can do. You can say, well, are you going to take k to infinity? Because if you're worried, you might say something like, you might worry about something like this. You say, well, yeah, you did that, but look at this. The number of gates also scales with the exponential of k, 5 to the 2k. So you don't actually do that. That's where what happens is you can then say what order of expansion optimizes it. So there turns out to be, when you do the number of gates, there's a minimum and then it goes up again. There's a unique minimum. And so we found that we're able then to optimize the k. And when you do it, then the number of gates doesn't quite scale linearly with t. There's a t and then an exponential involving the square root of the log of the time. So it's, but it's order 1 plus little o of 1. So it's very close to linear. So that turns out to be the case. I think what I'll do is, I'll give you a hint what I'll get to next time. So next time I'm just going to tell you why it can't be less than order t. So there's a lower bound. You could say, well, I mean, often I'll get a question that says, well, I can think of a Hamiltonian and come up with an algorithm that's even better than t. But remember that the point was that we want to be able to do, we want to be able to find an algorithm that will work for any Hamiltonian, even the worst case, and we can show that it has a cost of t and not more. This I'll cover next time. It's kind of cute because it turns out that in quantum computing and quantum information, lower bounds are very precious. People prove upper bounds on things on complexity. Lower bounds are very rare, and we found that we could use the lower bound result in quantum walks to prove this result. So it's a simple argument, but it took us 2 years before we were able to come up with the answer. So I'll go into that. I'll talk about the way that we color. And so in the lecture I gave on Saturday, I'm hoping to get to the point where at least you have a picture of how to take the quantum simulation and have an idea of how to map over a quantum simulation from an evolution that you want to approximate to an actual sequence of gates and how to convert them into an experimental language. Okay, I'll stop here. Wait till you get the mic.
We talked about quantum computing versus and reducing the complexity.
Yeah.
What about extending the notion of Turing computably itself? Can
I don't understand.
the notion of Turing computability itself, can problems that are not Turing computable using classical computers, problems that are not Turing computable, can they be computable using, say, quantum computers?
So the best I understand your question is you're
a
saying...
new class of problems,
I'll try again. The best that I understand your question is you're saying, can a quantum computer compute the uncomputable from classical? Is that the question?
What is now a subclass of what is now thought of as uncomputable?
No. No, we think that, we believe that, so assuming our beliefs are correct, we believe that quantum mechanics is computable. So any quantum computer that runs on quantum mechanics is not going to start computing the uncomputable. There were a set of papers that came out about 14 years ago. I forget, one was from New Zealand, and one was from New Zealand, the other group in Australia. And they started to make claims about this, but they were based on misconceptions to do with the fact that they thought of solving a wave equation. And it turns out that the wave equation, if you don't think about it carefully, deals with real numbers that are continuous. And if you start getting into a model of computing that's based on Bale, Shum, Blue, something like that, if you get into that one, then the whole notion of computability changes. So there are models of computing that change the game, but that's not what quantum computing is about. And those papers have since been buried and forgotten.
So, is there any relation between quantum simulation and quantum entanglement?
Any lesson?
Relation
between
quantum entanglement and quantum simulation?
Well, very loose. That quantum entanglement becomes useful as a resource to be able to effect Clifford gate operations by quantum teleportation. That's it. So entanglement has almost nothing to do with quantum computing in my view.
Is there an analog of the Turing's halting problem in the quantum regime when it comes to quantum computers?
Yeah, it's uncomputable. It's the same question he was asking back there.
As in,
It's completely analogous. It's uncomputable in both.
as in even the Hilbert's insidings problem is not solvable using a quantum computer.
If I say anything else, it'll be repeating myself. So it's uncomputable.
Okay, if there are no further questions, let's thank Barry again.